Okay, good afternoon. Today we'll be looking into linear programming problems, or LPP for short, and this is lecture 6B, which has been uploaded to Moodle. So as we discussed earlier, the structure of an LP problem is as shown over here. Uh, we have a maximize some objective function where the ci's are the coefficients of your objective function and the xi's are the decision variables. And they are subject to a bunch of constraints. So the constraints can be inequality or equality constraints. Inequality can be less than equal to or greater than equal to, and equality is as shown over here. And obviously, all the decision variables are assumed to be non-negative, because in linear programming, we assume that the decision variables do not take negative values. Variables like time, variables like cost, variables like profit are all assumed to be non-negative, okay? And so based on that, we can now, once we have our, so linear programming means the objective function and the constraints should all be in a linear form, okay? So they should be linear equations. So if we assume that we have L number of less than equal to constraints, as we see over here, so assume that there are L number of them, and you also have like R number of greater than equal to constraints. So in total, these two would be L plus R, and you have Q number of equality constraints. So in total, you would have L plus Q plus R number of constraints and N number of decision variables, okay? Okay. Okay, now what we have to what we need to understand about LPP problems is that they are always complex problems, okay? That means if there exists a local maxima or a local minima, then that would always be a global maxima or a global minima, okay? It may happen that you may have more than one I'm sorry, let's say global. You may have more than one global maxima or minima, but you should keep in mind that, so when you now we look at some examples where we try to visualize it graphically, and we see that for LPP problems, the feasible region will always be a convex hull. Now I would like to refresh your memory on what a convex hull is. A convex hull is like, for example, when we get to the figure, I'll show you, and that it would be easier for me to explain the definition of a convex hull. So what you need to know is that always the feasible region will be a convex hull. And once we have a convex hull, this guarantees that there would be a unique global maximum or minimum for that problem, okay? So there is an example over here as an example. So in the exam or in the quiz, I could just give you a problem statement. And what you have to do is you have to, like, I'll be giving you such a table, and you have to actually formulate the LPP problem using this information in the table. So in this example, we say that there are a bunch of food items that exist, okay? And for example, bread, butter, cheese, cereal, and diet bars. There are 5 items over here. And the content of protein, the amount of protein, fats, and carbs each of these items contain is also given to you in this table. And the cost of each of these, of 100 grams of each of these items in terms of dollars available in each of the food item is also given to you. So like, for example, for every 100 grams of proteins, the cost would be 0.25 cent, okay? So basically, this is it, and the total amount of grams from each of these items that you require to have, minimum amount that you need to have on a weekly basis, is also given to you over here. So the weekly cost, what you need is, you need at least 550 grams of proteins, okay? You need 600 grams of fat and 2,000 grams of carbs, okay, on a weekly basis. So what we want to do is we want to choose these items in such a way that the weekly cost that you have to pay for them is minimized, okay? So you want to pay the minimum amount of money so as to at least satisfy the minimum requirements of these food components in your food items, okay? So how would you do that? So basically, we have 5 items. So the first thing that you do is we say, okay, we will take 5 decision variables. So we'll have x1, x2, x3, x4, x5, and each of them will be representing the number of grams for each food item. So what I can say is, so since I want to minimize the cost, so I would say 25 0.25 times x1 plus 0.5 times x2 plus 1.2 times x3 plus 0.6 times x4 plus 1.5 times x5, okay, is my objective function, which I want to minimize, okay? And then there were some constraints, and the constraints are that 8% of this, that means 8% of x1 plus 25% of x3, x2 is not needed, so it is 0. 12% of x4 and 8% of x5 should be greater than equal to 550. Why greater than equal to? Because the minimum is 550, so it can be even more than that. That's good, but it should not be lesser than 550. That's why you have greater than equal to. So since we have 3 columns, we'll be having 3 constraints. And obviously, since x is the amount of grams, so it cannot be negative. It is either 0 or some positive value. And that's why we have this last constraint, which is all greater than equal to 0. So is it clear? Any questions regarding this formulation? I need an answer, please.
No questions.
Good. So another question, another example is about scheduling some, making some items in a factory or some company. So what you want to do is there are 2 types. So assume you have a car and there are 2 types of components in the car that you need to manufacture. And each of these components, they have to undergo 3 phases. One is tuning, milling, and grinding. Okay, so there are 3 operations on each of the 2 components. Okay, and these operations are done on different machines. So machine 1 does tuning, machine 2 does milling, and machine 3 does grinding. Okay, and the amount of time for each item is given over here. So it takes like a number of hours for tuning item. One object of type item A would take 60 hours, the other 75 hours, and the other operations 140 hours, okay? And the profit that you get by making each object of these items, part A and part B, is 120. So if I make like 10 objects, or I make 10 components of part A, it would be 120 times 10. Okay, so this is the profit I get by making or selling each one of those components from each type, part A and B, and this is the amount of hours I require to do the 3 operations on each part. Okay, so obviously what I want to do over here is I want to maximize my profit. If you want to make more money, okay. So I want to schedule these items in such a way that my profit is maximized. Okay. So obviously, over here you see that you have so the number of lots. So you want to know. So obviously, if you want to maximize this, so you have to make as many parts or as many objects of each component as you can. Therefore, the decision variables would be x1 and x2, which is the number of objects of type A and number of objects of type B that you can manufacture given these constraints. So what I want to do is I want to maximize the profit. So 120 times x1 plus 90 times x2 will be my objective function. And constraints over here, we have 3 columns, so there'll be 3 constraints. The first one would be the time taken for tuning machine A, which is 12 times x1. Okay, plus the time taken for milling machine A. I'm sorry, part A would be 8 times. I'm sorry, no, yeah, I have to go down. So amount of time for tuning each component of part A and B would be 12 times x1 plus 6 times x2. Okay, and this should be in total less than equal to 60. Similarly, this. Similarly, 15 times x1 plus 10 times x2 should be less than equal to 140. Okay. And obviously x1 and x2 should be greater than equal to 0. So once we have this formulation, then we can use either simplex method or the duality approach, which we'll be talking about. I don't know now or not, but I will try to speed up and see if we can talk about that today. And then once you have this problem, we have already seen some examples, or we have already studied about how to convert this into the standard form, then the slack form, and then solve it using the simplex method or the big M method. Okay, so we'll see that again. So again, this was another equation. I'm sorry, another example, and now we go to the graphical representation or solving these problems graphically. That means if you want to solve it graphically, your objective function should not be having more than 2 decision variables, because then doing it graphically would be difficult. You definitely have to use a software. But for problems which have two decision variables like the one we see over here, it's easy to actually see how it works graphically, okay? So we have a problem, maximize this function, and we have three constraints and the final last default constraint. So what we want to do is we want to see graphically what this means. So what I do is I take the first constraint, 2x1 minus x2 less than or equal to 8. So you first make it equal to 8, draw the line that passes over there. And that line would be, I guess it is this line, right? Can you see my mouse, guys, or no?
Yes,
okay, so this line over here is the equation 1, okay? Okay, so this is one constraint and it says less than or equal to. So everything less than or equal to, that means everything in this direction. When I've drawn this, the shaded line means that is not included, okay? So everything inside this, above this line. Then we have x1 plus x2, I'm sorry, x1 plus 2x2 less than or equal to 14. So that probably would be which line? x1, x2, 14. So I believe that is -1 and 1. Where's -1, 1? Which line is this? This is this, 2 minus.
The one with negative slope, I think.
Huh? Minus.
You're asking about the third equation?
The second equation.
With a negative slope.
Less than
4. DC.
1, 2. So -1, 2. So when you, I cannot think now. When you have these three lines, okay, what you basically have to do is just draw those lines. So these are the three lines, okay? And when you have x1 and x2 greater than 0, obviously it is this x-axis. x1, this is x1. Sorry. x1 and this is x2. So basically, the shaded area is the feasible region that you have, okay? And now what I have to tell you is the convex hull. So what is a convex hull? If you look at this guy, and I've told this before, but I'll repeat it again. If I take any 2 points in this region and I connect them with a straight line, all the other points that lie on the straight line should also be inside this region. That's a convex region. A convex hull is a region of this form. It means that it has angular endpoints. As you see over here, the endpoints A, B, C, D, E are the angles, so they form polygons, okay? Problems of the form of polygons, so this is in 2D. When it becomes in 3D or 4D, they form higher hyperplanes of planes with higher dimensionalities. But to visualize what a convex hull is, assume that you have a rubber band, and each of these endpoints over here, A, B, C, D, E, they are pins on a board, okay? And what you do is you put this rubber band around this. So assume that I put the rubber band around these points. So if the rubber band touches each and every endpoint that you have on the board, then that would be a convex hull. Okay, so if I had a point over here, say X, okay, and the rubber band doesn't touch X, it means that definitely this is not a convex hull, because in that case, you would have such a thing. And if I take, let me change my color. So in that case, I would have this D going to X, point X, and X going to C. And then if I take any 2 points, like for example, these two, and I connect them, you will see that there will be some part of the line which is outside this region. So it would not be actually a convex region, okay? So this is a convex hull. So whenever you want to think about a convex hull, think about it as a rubber band and the pins that you have on a board. So the rubber band should touch or be in contact with every pin that you put on the board. Okay, is it clear? Guys? For those of you who send me email that you do not understand, is it clear? Why is no one answering?
Yes, it's clear.
Okay. So if you want to write this in the matrix form, you write the objective function as this, where we take the coefficients 2 and 1, okay? So this coefficient and this coefficient, which is 1, you put it in this form. This will become your C transpose, and the decision variables in a column vector form. So you can write this whole thing in the form of a matrix, which would be this. So again, over here, you take the coefficients on the left-hand side, put them in the matrix A. You have your decision variables X, and they are equal to D vector, which is on the right-hand side. Okay, so this is what is the matrix form representation of a LPP problem. Now, forget about these red lines or these vectors that are drawn over here. That will be needed when we get to the KKT problem. Okay, so actually over here I've briefly mentioned about it. So this vector C that we have over here, so what I did is the objective function, I took the coefficients and I put it as here, and I call the C transpose, okay? And when I multiply it to this vector, this column vector of decision variables, it would give me my objective function. So this C that I have over here is called the gradient of the objective function. Okay, and what do you mean by gradient of the objective? I told you that the gradient of a function is the vector which always points towards the increasing direction of the function. Okay, so for example, if you have x1 greater than equal to 0, it means that if you look at x1, it means that everything above this, right? Am I right? And
Yes.
if you have
Yes.
x2, means everything to the right of this. So this is what is this? The direction in which the value of x would be increasing, or x1 or x2 would be increasing. Okay. So if you look, you see that the gradients of the constraints. So we have written the constraints also in this form. We have 3 gradients: 2 minus 1, 1, 2 minus 1, 1. So if you look over here, 2 minus 1 is the gradient of the constraint 1, which I told you is this line. 1, 2 is the gradient of this line. So the second constraint is this line, which we drew over here, and the gradient would be in the increasing direction. And minus 1, 1 is, where's minus 1, 1? Well, obviously this guy. This guy or this guy? Oh, no, this guy. Okay. And this is showing you, and this is 2 minus 1, which is shown over here. So it's in this direction. So obviously we see that these are the gradients for the constraints, okay? And it's written over here for the bounds. Recall that the gradient is normal or perpendicular to the boundary and points in the direction of the increasing function value, all right? That is something that you have to keep in mind, because we'll be needing that for the KKT analysis. Now, so what is the good thing, or what is the very unique feature about LPP problems? Why are they easier to solve as compared to any other class of optimization problem? It's because that because we proved that mathematically, it's proved that LPP are convex, and if it is convex, it means that to find the optimal value of the problem, you only have to look or evaluate the objective function at the endpoint. You do not have to worry about it in the center. Okay, so there's a theorem which we won't be looking into, but there's a theorem which proves that for LPP problems, the optimal value of the objective function will always exist at one of the endpoints. Okay, and that's why it's very important for us to make sure understand what a convex hull is. If it's if you have 2 variable decision variables, easy to see that, but once the system becomes multidimensional, probably we cannot visualize it that easily, and therefore we have to use the KKT condition to ensure that we have reached optimality or not. Okay, to do that, we need to understand what the gradient is. So every point in the feasible region, which is this region over here, will satisfy all the constraints in the problem, obviously. So all the points, including the points on these lines, will, because it's greater than or equal to, will satisfy these 4 constraints. Okay, 1, 2, 3, and the last constraint. Okay, hyperplane with polygon with good. Okay, that's it. Okay, so that's all you need to know from here. Standard form of the LP. Well, I told you about how to express something in the standard form if it is less than equal to what you do. Tell me. If you have a constraint of type less than equal to in an LPP problem, how do you convert it into equality? guys? What's wrong today? Why is no one answering? Are you all going to Shymkent?
No, not really.
Okay, so if I want to change this guy into an equality constraint, what do I do?
We should introduce Slack variable.
Yes, I introduce a Slack variable. So this is less than equal to, so I just introduce say S1 and I equate it to -2. Okay, but again, you have to keep in mind that the right-hand side is a negative. These should be positive. So you have to multiply both sides by -1. So basically this would become minus x1. This will become minus x2 minus s1 is equal to plus 2. Okay, so always the right hand side should be positive. Keep that in mind. Second thing, okay, so if you have another constant which is greater than equal to, and I told you what you have to do is you not only add a surplus variable, okay, but I'm sorry, you not only reduce or deduct a surplus variable on the left hand side, but you also add an what we call auxiliary variable a1. Okay, so if it is greater than equal to, you add an auxiliary variable. All right, we have seen this in our earlier lecture. Another thing that I don't remember whether I've talked about it or not is if in the default condition there is no explicit mention that x2 is greater than equal to, so it is unrestricted. That means x2 can take even negative values. If this is the case, so this is obviously not in the standard LPP form. You have to convert it. It means that we have to define we have to convert this x2 into some form such that this will always be greater than equal to 0. Okay, and I think I discussed this, but just to remind you, what we do is instead of that, instead of x2, we replace x2 with 2 new variables. So I can write x2 as y1 minus y2, where y1 and y2 are greater than 0, such that their difference is equal to x2. And that way, if I replace it, so the new updated standard form representation would be as shown over here, everything converted to equality and all the decision variables and all variables actually greater than equal to 0. And we have a maximizer. This is all we need, okay? Is it clear, guys?
Clear.
Good. And we know that if you want to write, keep this in mind, the matrix form is very important because we'll be needing the matrix form in KKT analysis. Okay, so in matrix form, when standard form and everything converts to equality, and if you want to write it in the matrix form, it will again be just transpose matrix of C times the column matrix X, and the product of AX is equal to B, where B should be positive, and all the variables should be greater than equal to 0. Now we'll look at the simplex method, and we assume that in our simplex method, we have only constraints of the form less than equal. Okay, we do not have equality, we do not have greater than equal. If that's the case, on page 3, so if you look at this constraint, this guy, everything is less than equal to, right? These 3 constraints. So what you have to do is you just add the slack variables, which is plus s1, plus s2, plus s3. In each of those constraints. So basically, if I do that, this is what I get. I add x3, x4, and x5. Let me choose a nice x3, x4, and x5 as my slack variables, and I equate it. And therefore, I would get this. Remember, the slack variables do not come in your objective function. It's only the auxiliary variables that you include in the objective function. Okay, and so now we have a form that we can actually apply simplex method on. So if I want to again express this in the matrix form, the C variable would be 2, 1, and 0, 0, 0 for the slack variables, because in order to make the dimensions meet, you just put them equal to 0. So I could have written this as plus 0 times x3 plus 0 times x4 plus 0 times x5. Okay, so you put the coefficients, okay, which is over here, and then the x column vector would be the vector column for the column vector for all the variables that you have, including the slack variables, and b would be the right hand side of the constraints, and a would be the coefficients of the constraints, which is given over here. Okay, remember that well, yeah, so this 0, 0 is actually this for x4. This is x5. And this is x3, x2, x1. So you just fill in up and you will get it in the matrix form, okay? Okay, so once we see this, we look at this and we see that, okay, this guy is in they are linearly independent. That means these three guys, no two constraints can be written in the form of the third constraint. So they are linearly independent of each other, and therefore we know how to find the rank of a matrix. So the rank over here is equal to 3. So there are 3 linear equations which cannot be written in the form of each other, okay, by any addition or multiplication operations. And therefore, so when you have this, therefore the number of solutions would be the 5 variables minus the 3 linear, the rank of the matrix, which will be equal to, that means we have to set 2 of these decision variables is equal to 0, and that would be our basis feasible solution, and we start our simplex method from that solution, okay? So basically, since we have to only set 2 of the variables as 0, what we do is we choose x1 and x2 to be equal to 0, so that objective function will be equal to 0, and then every time we remove and we enter the variables in a simplex method so as to maximize or increase the value of the objective function to some positive value other than 0. Okay, so initially if I set x1 and x2 as 0, then we see that x3, x4, and x5 would be 8, 14, and 4, okay? So the basic feasible solution would be basically just this, and the objective function at this point, the z value would be equal to 0. So now over here, we see that the basic variables over here are the slack variables that we had introduced, that means these 3 guys. And the non-basic variables are the variables x1 and x2, which were equal to 0. Okay, now let's look at the table that I have defined in our paper over here. So what I've done over here is I've written all the variables over here, x1, x2, x3, x4. I'm sorry, x1 to x5. And the first row, which is this row, I have taken it to be the objective function, the cost row, I will call it. And the cost row includes the coefficients of the objective function, okay? And then on over here, RHS means right-hand side, and right-hand side basically is the B matrix, the B column vector, which is this guy, 8, 14, and 4, okay? So I put this over here. The cost function has no thing. Remember that this negative over here is, do you know how we got this? It was maximize some Z equal to, I don't know, 2x1 plus x2. So we take this to the left-hand side, and therefore this becomes minus 2x1 minus x2 equal to 0, and that's why we have a 0 here, and this is minus 2 minus 1, all right? Last time the video that you showed that they also had a column for z, but we do not have it over here because z is not what we're playing around with. Okay, so basically this is my cost row. This is the what we say, the variables, the non-basic variables, okay? And the non-basic variables or the slack variables that we introduced. And now when we put in everything, what you have to do is, this is what you do, okay? I've written the details, I've written it in words, but just to make it short and to do it quickly, you look at the cost row, which is this row, okay? Look at the elements in the cost row. As long as there is an element with negative sign, you do the simplex method iteratively. So simplex method is an iteration method, okay? So, and okay, so we see over here, we have 2 negative elements, -2 and -1. You always choose the element, or you always choose the column, okay, in which the negative element is the least element, okay? So if you see that -2 is lesser than -1, okay, so you would take -2 as your first column. So that means I choose this column, the column containing -2, and now in this column, okay, I have to select a row. And how do I select that row? So again, once again, I repeat, to choose your pivot column, what you do is you look at the functional cost row, the row corresponding to the objective function, and you choose that column which has the, if like you take the absolute value of this, which has the biggest magnitude in terms of negative. It should be negative, okay? And among the negative elements, the one which has the biggest magnitude, which is -2, okay, or the smallest element, I could say. So over here, this would be the first column. Now within the first column, you have to choose one of these three rows. You do not choose the objective function, the cost row, okay? Then you look at these three rows. Now we have to choose one of them. How do we choose our pivot row? What you do in the pivot row is that every element in this column that you have chosen, pivot column, okay? You take that element over here, it's 2. You go to RHS, you have 8 over here, which is the B vector value, okay? And you divide 8 by 2. 8 by 2 will give you 4, okay? Do it for the next one. So over here, you would have 1, 14. So 14 divided by 1 is 14, all right? -1, 4. -1, 4 divided by -1 will give you -4. And then you choose the row which has the greatest value, the division value. So we see that, I'm sorry, well, over here, you do not do this -4 because this guy is a negative, so you do not take this. So if it's negative, you can ignore it. Sorry about that. So if you see if it's negative, we do not actually do the division 4 divided by -4 because that would not give us the answer. We only take the positive elements and you divide them with the RHS value, which is the value in the B vector of the equation. 8 divided by 2 is 4, 14 divided by 1 is 14. So between 4 and 14, we see that this guy is lesser. So we obviously choose this as our pivot row. So we have a pivot column, we have a pivot row, we meet at this point, which would be our pivot element. So the pivot element is the element which decides on which variable will be leaving and which variable will be entering the table. Okay? Is it clear so far?
Yes.
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 Thank you. Just let me have some water. Okay, so once we have that, we now what we have to do is, can you tell me what's the next step? What do we do next? Once we found the pivot element? We do the elementary row operation or the row elimination operations, which means that you have to make that pivot element 1 and every other element in that column as 0, right? It's the same thing that that guy did in his video, but the table was structured differently. The ones that I have used, the table that I have used also just the same thing, but with slight modification. Over there, his row, his cost row was at the bottom. Over here, we have put it at as the first row, and so just slight difference. So basically, you do the ERO. We call it the elementary row operation. It means that you try to add or multiply. You use these rows in order to make all the other elements in these three rows, not the cost row, 0 and that pivot element as 1. Okay, so if you do the operations, you would get this. Okay. 1 minute. Let's read and see what has been done. Yes. Okay, so now that we have done that, so once we see that, okay, in this pivot column, we have our pivot element as 1, the others as 0, then we go again to the second iteration of the simplex method. We look at the cost row, we see if there is a negative element. Yes, there is 1. And since this is the only one, we now focus on this column. Now this would be my pivot column. Now we have to find the pivot row. The pivot row would be the negative value you ignored. So you have 2 positive values, 5 by 2 and 1 by 2. So you divide 10 divided by 5 by 2, which will give you, what will it give you? 5 by 2 to 10, 20, 10. It would give you 10, right?
4.
I'm sorry, 20 divided by 5, 4. Yes,
4.
it would give you 4. And this would give you 16, right? No, this would give you, 16. Am I right?
Yes.
So this guy, why haven't I written all this? I don't know. Well, okay, so this would give you 4, this would give you 16. So obviously the one which is in the red brackets would be your pivot element. So this is my pivot row, and this is my pivot column, and therefore this guy would be my pivot element. Now I have to make this guy 1, and this 0, and this 0. Okay, so again, using ERO, you can just do this. Okay, then again, we go for the third iteration. We see the cost row, there is no negative element. So this tells us that we are done, we can stop. And so since all the coefficients over here are positive, we can say that, okay, no, I forgot to tell you about the entering and leaving variables. I think we discussed about this. So for example, over here, this guy, x3 would be the entering variable and x1 would be the leaving variable. What it means is you just put x1 in place of x3, okay, as you see over here. And then again, since x1 was here, it replaced x3. Now we replace x1 with x2. So finally you would have x2 over here, and therefore now what we can tell you is that, okay, so for x1 would be would take, so now once we are done and all the values are positive in the cost row, what you have to look at is you have to see, okay, x1 is equal to 6, x2 is equal to 4, x5 is equal to 6, whatever is remaining is equal to 0. Okay, so you would have this as your solution. Okay, so if you plug in this into your objective function, you would get a total objective value of 16, which is the maximum value this guy could obtain. Okay, and that's it. So this is one example of simplex method where the constraints are of the form less than equal to. So this is the summary, the 4 steps that are included. Well, let's look at now the cost row. Let's focus on the cost row. Okay, so recall that the gradient of a function is normal to its counter and points in the direction of the increasing function value. So in this example that we just saw, it is obvious that the point A is not the maximum. Why? Can you tell me? Where's that figure? This point. So this is not a maximum, this point. Why?
Because the value of function is at that value.
Yes, because if you look at the gradient of the objective function, which is C21, which I've written over here, I don't know, this guy, you see this guy? So if you draw this vector, unit vector, okay, in form of a unit vector, so this multiplied by a unit vector would give you this. And so this is telling you, okay, the function is increasing in this direction. Since this is a maximized, obviously this guy would not be the optimal point, okay? So that's very obvious, correct?
Yes.
Good. Where are we now? Now, let's look at point B. So basically, if now what I want to tell you is now, okay, so let's see what solution we got. From our simplex method, we got the solution of which one is the best point? I think this point is the best point. C would be the best point. Let's look at C. This point is the best point, okay? So at this point, you see that this C, gradient C, which is the gradient of the objective function, if you rewrite it over here, you would see that there is no point at which you can still stay in this convex hull and further increase the value of this. So if I go to any other point on this line, say this point or this point, you see that this leaves the feasible region. So the last point that leaves the feasible region is this point C. Okay, and I told you that another way to draw it actually is so there are 2 ways to graphically find the optimal solution in LPP. One is to obtain this region, feasible region, okay, find the endpoints and just evaluate the function, the objective function at each of these endpoints. Whichever one gives you the highest one is actually the optimal point. Another way is, again, plot these lines, find the feasible region, but then again, what you do is you plot this objective function, which is, where's my objective function? Which is 2x1 plus x2. Okay, so what you do is you draw the line 2x1 plus x2 is equal to 0. Okay, so what will happen over here, and if you do this, so this is an increasing, so you will get some line, you'll get some line for 0, so which is passing through point 0. So this is at equal to 0. If you change this coefficient to say 2, you will get a line which is parallel to this at equal to 2. And you keep doing this, so at some point, some k value, which you have over here, positive k value, this line, you'll get a parallel line, which is at point which intersects at this point C. And that k value would be your optimal value for your objective function. In this case, it was equal to 16, which we found. Okay, so I would have 2x 1 plus x2 equal to 16. So that means my z, which is my objective function, can take a maximum of 60 given these constraints. Is it clear, guys? If you understand it graphically, I think it would be easier for us to explain the rest. Okay, is it clear? Do you want me to take names,
Yes,
or
yes,
just reply, please, someone? Otherwise, I feel like you all are going to Shymkent, only I'm stuck in Astana. Okay, so now let's look at what KKT is. KKT is, there are 3 guys, genius guys, who came up with the conditions. So one way of solving a problem, a simplex problem, as I told you, is iterative. So you keep doing this until your objective function, all the elements in your cost row become positive. If you have less number of decision variables, then that's easy to check, but we need some general condition to guarantee that the value that we have found is actually the optimal solution. So I ask you to solve something using the simplex method. You solve it, you get this the solution that we just saw in this example. Then I should ask you to, okay, prove that the solution that you got is actually optimal. Okay, that there exists no solution better than this. To do that, what you do is there is a mathematical approach, which is KKT, which was founded by these 3 people, and it actually tells whether that point that you are talking about is optimal or not. Okay, and when the dimension of your problem increases to n number of decision variables, again, you can just use this equation and it can simply prove the optimality. Okay. So this KKT is not only used in LPP problems, but also in nonlinear problems. But I don't think we'll be touching nonlinear problems in this course, because that would get into regression and something that I believe should be taught in some other course like machine learning, or I don't know, pattern recognition. But for this, we'll be focusing on linear programming, and in linear programming, we'll see how to use this KKT. And KKT is also used to, so what I can do is, if you have a problem, an LPP problem, another good thing about LPP problems is that every LPP problem has a dual. That means I can convert an LPP problem with large number of decision variables into an alternative form with lesser number of decision variables. And why is it important? How is this cool? This is cool because if you have large decision variables in a table, then you have to write a very big table and you have to solve it for each and every decision variable, which is very time consuming. What I can do is I can convert it into its dual form, which would have a form with lesser decision variables, and then solving the lesser decision variables would obviously give us the same solution. Okay. So we'll be talking, it's a very cool thing. And if you think about, if we understand and look into it in more details mathematically, you would see that how useful it is in solving many problems. Okay. So these cool techniques actually, they make sense or they shine when we have larger dimensions of problems. For 2 or 3 dimensions, you might say, it's okay, we can do it by using simplex or M method. But when the number of dimensions increases, as the dimension increases, using the duality theory is very, very important. Okay. Okay, so let's see. So briefly, I just want to explain. So basically, what is KKT? KKT is a mathematical form, or it's an analytical form to prove whether a given point is optimal or not. Okay, that means whether this is the, and I told you in LPP, one optimal solution would obviously be the global solution. One local optimal solution will be the global solution. So since it's a convex hull, as I told you, we should only evaluate the objective function at the endpoints. Even though the feasible region, there are points which satisfy all the constraints, but they are not our optimal solution. Okay, keep that in mind. Optimal solution means the solution or the point which gives us the highest objective value. All right. So what I
Yes.
can do. Good, thank you. So what I can do is the cost gradient, which we saw earlier for this example. Let me bring it for you. Now, what I want to do is I want to generalize this thing, the red vectors shown over here, into n dimension. Okay, so we saw that the gradient. The cost gradient means the gradient corresponding to the cost function or objective function would be 2, 1, right? Which was the line that we drew over here with k is equal to 0, and then we shifted this line until it reached point C, and it gave us the value of 16. So the gradient of the cost function, which we call the cost gradient, which is 2, 1 in this example, can be expressed in this form. Can be expressed in the form of a summation of mu i's times ni, where this I, this capital I over here, is a set of active constraints. What do you mean by active constraints? So we have, for example, let's go back to this example over here. So we have how many constraints? Basically, we have 1, 2, 3, 4, 5. These 3 constraints are the constraints equated as 1, 2, 3, and this constraint, the last constraint. So we have 5 constraints, okay? And if you look at the objective function 2, 1, so if you take the objective function at 2x1 plus x2 is equal to 0, you would see that it is the active constraints at that point A, would be this constraint and this constraint. So the other constraint, they did not play any role in at this point A. So you look at point A, the constraints that are involved are this x-axis and the y-axis, right? x1 and x2. So that's why we say that they are not, so such constraints are known as the active constraints. So if you look at point D, the active constraints are the line, this line and this line. So these 2 lines would be the active constraints at point D. At point C, it would be this line and so forth, okay? So that's the definition of active constraints. Now going back to here, so we take all the points I at which there are active constraints, so basically at all the endpoints, okay? And Ni is a gradient of the ith active constraint. So what we do is we define a mu I, which is a Lagrangian multiplier, okay? And we have the n, which is a gradient at each of these endpoints, okay? So basically at each endpoint, you have a Lagrangian multiplier, okay? So basically, it's saying that the C, the cost gradient, okay, it lies in a cone, or it lies in a region, and this region is formed by the gradients of the active constraints. So you don't have to worry about this. So if you have less than equal to constraints, then the equation 4, this equation, must satisfy for all the values, all mu I values for which this should be non-negative. So mu I should be always non-negative for the less than equal to constraints, okay? So let's go back and look at the example. Let's look at the active constant. So in this example, the active constant gradients at point A, we saw that point A means the x1 greater than equal to 0 and x2 greater than equal to 0. So if you write the constraints at those points, it would be -1, 0 and 0, -1, right? I'm sorry, if you write the gradients at these points, the gradient at point x1 and x2 would be -1, 0 and 0, -1. Okay, we showed it over here. These 2, right? Gradient will always be this. Good?
Yes. Yes.
Good. Where is that? Where did we go? Oh, here it is. Okay, so then what you do is what you can do is now we want to see. So we had let me write it down actually over here. Let me use a nice color. So we had our cost. So look at equation 4. What was equation 4? Let me go up this guy. So equation 4 is saying that the cost gradient can be written in the form of some summation of product of mu i's into the active constraints. So basically, let me rewrite this. For the point A, it would be something like this. So we write the cost gradient, which is what is it? 2, 1 was it? Yes. The coefficients in the objective function is equal to mu1 times the gradient at one of the constraints. So we have the constraint, the first constraint is -1, 0, okay, plus mu2, okay, the second active constraint, which is 0, -1. Right, so we're looking at point A. At point A, there are two gradients that are involved, okay? So this is one gradient, this is the other gradient. These are the gradients corresponding to the active constraints, and then you multiply them with some mu value, which is the Lagrangian multiplier. So if you solve this, what you would get 2 is equal to mu1 times -1 is minus mu1, right? Mu2 times 0, which is equal to 0. So 2 is equal to minus mu1. So mu1 is equal to -2. Okay. And the second one would be 1 is equal to mu1 times 0 is 0. Mu2 times -1 is minus mu2. So we see that the mu's that we get over here is -2 and -1, and they are negative. But we have said that for less than equal to constraint, they should always be non-negative. So obviously A is not an optimal point because it doesn't satisfy this condition. All right, is it clear? So as per KKT condition, point A cannot be an optimal point. Is it clear, guys? Any questions?
Yes, it's clear, no questions.
Good.
No.
Then you do the
Okay.
same thing at point D and C, and you see that even at D, you would get mu1 and mu2 to be, one of them will become negative. So both of them should be non-negative. So if this is negative, it means that again, this is not optimal. You do it at C, you will see that you get mu1 and mu2 both positive. And since both are positive, so this would guarantee that the point C that you have found using the simplex method is actually the optimal solution. You cannot get better than that, okay? So that is the use of KKT in terms of gradient. So whenever you want to use KKT, you should remember for less than equal to constraint, you should remember this equation 4. Okay, so you should be able to write the cost gradient in terms of the sum of the product of Lagrangian multipliers and the gradients at each of the active constraints. All right. Now let's see what happens if we have greater than equal to. So if you have greater than equal to equality constraint, this is when you add the surplus variables and the auxiliary variables, okay? So assume you have this problem over here where you have 3 decision variables and you have 3 constraints and the last default constraint. This is not in the standard form. We convert into the standard form. Less than equal to means you add a surplus variable. Greater than equal to means you deduct, I'm sorry, less than equal to you add a stack variable. Greater than equal to you minus a surplus variable and add an auxiliary. Equality, you just add an auxiliary variable. All right, we have discussed this earlier. So if you write it in the standard form, this is exactly what you would get. So if you look over here, so when it comes to so when you have an auxiliary variable it's involved or comes into play when you actually have greater than equal to or equality constraints. So when you, in that case, with a standard form, will always have an auxiliary variable, and to solve LPP problems with auxiliary variables, we talked about the big M method that we saw last time, we can use big M method to solve that problem. But, and I also told you, so basically what I want you guys to do is I want you to try to solve this problem using the big M method. I have not done it over here. I've used another method, which is a two-phase approach, and I'll tell you why. I want you to do the big M method, which we know that you have to include minus M times the auxiliary variables that you have added. right? And then you solve that, and then once you did get rid of the auxiliary variables, you can again solve using the simplex method. Just follow the video that we saw last time. That is using big M method. So basically, big M method or a penalty method is a method where we give a very, very large penalty, which is big M, to the auxiliary variables because we do not want them to have any impact on finding our solution. Okay, so we give them some very great value, and then in the end, we try to minimize it. The problem with the big M method is that unless the problem that you're solving is small, it contains just 2 or 3 decision variables, it's okay. You can do it in a tabular manner manually. But when you have many decision variables or many constraints, I would say, with greater than equal to or equality signs, then using big M method manually would be very difficult, and it would be very time consuming. So that's when you go for a software or a computer, or what we say, machine approach. Okay, so you try to solve it using simulation, numerically using a machine. Okay, so and again, the problem with that is, even though it saves you time, the problem is we do not know what value we need to choose for M, because in the machine you cannot just write M. You have to give some, or you have to give a very, very big value close to infinity for M. But in machines, if you have very multiple auxiliary variables, it may happen that the auxiliary variable that you get or you eventually end up with would be very large itself. And therefore, you should be able to differentiate, distinguish between the minus M and the very large value that you get for the auxiliary value. So again, even doing it using the computer is kind of challenging if you have, as I said, many auxiliary variables. Okay, so the other approach is to overcome this problem. The problem is that what value should be assigned to M. Okay, so to overcome this problem, there's another approach, which is a two-phase approach. It solves the problem in 2 steps rather than assigning a minus M value to the auxiliary variables. Now we'll be looking at the 2-step or 2-phase approach. Okay, any questions so far? Okay, so in the 2-phase, okay, in the 2-phase approach, what we do is, so over here you see basically what happened is, oops, 1 minute. So where's my equation? Okay, so over here, basically, we should add x4 over here, okay, which is added over here. Then this is greater than, so we minus x5, which is a surplus variable. And over here, we did not do anything. So basically, if you look over here, we have not added the auxiliary variables, right? So we need to add an auxiliary variable here. And we need to add an auxiliary variable here, because this is the greater than equal to equality, and this is the equality or constraint. Okay, so these two we have to add, whether it's the big M method or the 2-phase method. So now what I've done over here is I've said, okay, now we add x6 and x7 as the auxiliary or artificial variables to these 2 equations. So now this will become a minus x5 plus x6, and this will become plus x7. All right. So basically, this is what it will look like. So you have x6, x7, and now you have your problem in the proper form. And now what we do is, keep in mind that we have this guy. Look at this minimization. I am not minimizing my objective function. My objective function was different. This was my objective function. In the 2-phase approach, you minimize the auxiliary or artificial variables. So I will write minimize x6 and x7. So I want to minimize these 2 values because I want their effect to be as minimum as possible on the objective function, right? So I minimize the values of x6 and x7, okay, subject to these 3 constraints. Is that clear? If I wanted to use the big M method, what I would have done is I would have actually included minus m x6 minus m x7 in the objective function, right? But here I'm not doing that. It's in the 2-phase approach. You do not include it over there. What you do is you just minimize the linear combination of x6 and x7. Harasha?
Yes.
Okay, so great. So now what we have is this guy. We want to minimize this subject to this. So we put this in what is this? In the tabular form as we have seen earlier. So now what we want to do is we want to make it so this is the coefficient of the auxiliary variables. So x1, x6, and x7 is 1, 1, right? So now what we want to do is we want to make this 0. All right, we want to make this 0 because we do not want to, we want to minimize it. So we do not want this actually to be anywhere. We want to remove the auxiliary impact of auxiliary variables from our constraints. So what we do is to make them equal to 0, what you have to do is you do the ERO again, and using, so it says that the last two equations, that means equations 8 and 9, these two equations, okay? So you subtract these two equations from the first equation, okay? So you would have this. So you can use 8 and 9, that means these two equations, okay, from the tabular form, and you can remove this 0 from the first cost row, okay? And so when you do that, your F value would be, if you write x6 and x7 in terms of equation 8 and 9, this is what you would get, okay? So instead of x6, I have written everything in terms of, so x6 on the left-hand side, and everything else on, I take this whole thing to the right-hand side. And again, for x7, I take this whole thing to the right-hand side. Okay, when I replace it for x6 and x7 in the table, this is what I would get, the coefficients, right? So my F function would be modified, and I would get minus x2, minus x3, plus x5, plus 3. Okay, so this 3 would be basically this if you take it. And remember that you have to take this whole thing to the left-hand side. Is equal to, the right should always be a constant. So this would be equal to minus x2. Over here, you see that what I've done is instead of 3, I've just written minus 3, doesn't matter. Or I've just taken F here and I've taken this guy to the other side, doesn't matter. So minus 2, minus 3, 1, minus 3, okay? And then once we do this, we apply the method that we just saw, which is you look at the row column which has the greatest minus value, which is minus 3. Take the division, that means 8 divided by 2, which is 4, 2 divided by 1, which is 2, and 1 divided by 2, which is half. So this is least. So I take this row and this column, and this is my pivot element. And I do the same thing for this until all the values in the F function would be non-negative, right? So at this point, we see that when x1 is equal to 1, let me clear this off. When x1 is equal to 1, x4 is equal to 0. I'm sorry, no, x1 is equal to this one, x4 is equal to 4, and x3 is equal to 1, okay? The functional value becomes 0. The minimum value that we had for x6 plus x7 would actually become equal to 0, okay? After we do this, now we begin the second phase of the two-phase problem, okay? So what we do is, so these two guys, we can just ignore them, remove them from the table, because now we do not, because we have minimized the values, we have found the functional values of the variables for which x6 and x7 become, minimize the functional value to 0. So we remove these two columns, we are left with these, the remaining columns. So you see, I have done the same thing over here. So once you're left with this, and then what you do is you plug in the original objective function. So if it is maximization, you would see that you have -1, -1, -2. Okay, so we remove these and you put in the plugin for the original. Where's the original guy? This one. Okay, so again, you have to take this. So this is z equal to this. So you take everything else to the left-hand side. So we go -2, -1, -1. Clear? When you do that, this is what you get. Again, you apply simplex method. This would be great. This is the pivot column, pivot row. You solve it, make everything else 0 except that guy should be 1. You keep doing this iteratively till all the elements in the row column, in the cost row would become non-negative. Okay, so the next would be this guy. And you see that everything is now 0 or positive, and that's when we are done. Then over here, I can say that x5 is equal to 2, x1 is equal to 7 third, and x3 is equal to 5 third, and the functional value that you obtain at this point would be 17 divided by 3. Okay, and this would be your optimal solution. Is it clear? So the two-phase problem is another approach which you can use, or you can use big M method, doesn't matter. But the advantage of two-phase is it may be a bit longer, it may take more time. But if you want to program it, it would be very efficient, because then you do not have to worry about what value the big M should take. Okay, both approaches would give you the same answer. So that's why I asked you now. This is a two-phase method. I solved this. Now try to solve the same problem, okay, using the big M method that we have seen. You would see that you would get the same answer. Please do it at home and try to solve it. If you cannot do it, send me a solution and I'll tell you where you've gone wrong. All right. Then in the end, I've given you what are convex sets, what are non-convex sets, and this is a proof of convex function. What else do we have? Yes, so these are some examples where I've asked you to write this in the standard form and find the solutions to this, guys. So you can just look at this. This is an example of an unbounded solution. So that means the constraints, they do not close a convex area. The area is unbounded and you have multiple optimal, infinite number of optimal solutions. Similarly over here, the two-phase method. This is an example where I ask you to solve this using the two-phase method, and the answers are given to you over here. So tabular form, you have to think about how to do it, okay? So for example, over here, since the value of M, we do not know in the program. If you want to program it, you can take the number. So you want to know how many times you need to iterate over the big M method. You can do the iterations over some value which is greater than equal to M, but again, there are other ways to find out, and the other ways are that if you find the functional values at each of the endpoints, you can take the difference and see whether their relative difference is less than equal to some epsilon value, very small value. If the increase in the optimal function is very small, you can assume that that's the point. Okay, and that's it. That's it. So these are just some points, tips in case you need to implement. That's all for today. Tomorrow, next time, we will be talking about KKT conditions, and we'll be looking at how KKT conditions can be used to confirm or guarantee that the solution that you have found is optimal or not. I will be giving you some more examples. Okay, so you have homework, where in your homework you'll have to solve many LPP problems using big M method and two-phase method. Okay, so I'll give you different types of problems, unbounded, bounded, where you have to know how to convert them into standard form and solve them. And always in the exam or when you're solving, always check. Okay, so if it is like a problem with two decision variables and I ask you to use big M method, you solve using big M method, but you know that to make sure that your solution is right, you just graphically represent it and check and see if graphically it makes sense or not. And graphically, as I told you, it can only be the solution. The solution always exists only at the end point, so you don't have to worry about any other point. Okay, so always do that, whether it's the exam or whether it's your homework, and check it. But if it's for large number of decision variables, probably you will have to be very careful when you are doing the tabular approach. Okay, because any small mistake with the plus or minus will screw up everything. All right, any questions?
No questions.
Good. I hope you guys are studying, and please study. If you have any questions, please drop me an email, and I hope I've been able to explain the LPP problem using big M method and two-phase method properly this time. If you still have questions, you can drop me an email. We could meet up and I can maybe write a small example and show you how it would answer your questions. Okay. Happy Nowruz in advance to all of you, and take care of yourselves when you're traveling, and I hope to see you guys very soon. We'll obviously meet on Thursday, but after Thursday you guys can enjoy your new year. Okay, if that's it, we can stop.
Okay, thank you.
Thank you, sir. Have a good time. Thank you. Take care, everyone. Bye-bye.
Bye.
Thank you. Goodbye.
See you. Bye-bye.